The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone, and welcome to Burp Process Equipment's webinar series on containerized systems. I'm Mark Turgenti, the Director of Design Engineering and Business Development for Burp Process Equipment. I want to welcome everyone today. For those of you who are used to our webinar series, today's topic is a little bit different. Typically in these series, we discuss different water and chemical technologies, and today we're going to talk about really a different way that these systems are built. So before I get into that, just a few things we want to kind of bring up. This webinar is being recorded and will be sent out to those in attendance. Further, this is going to be kind of a casual event, so if anyone has any questions, please feel free to type them into the chat window, and we will try to answer them during the broadcast, or we will answer them after the broadcast via email. There will also be a short poll question asked throughout, which is completely voluntary to answer, but helps in keeping the interaction with the webinar. And as always, at the end, if anybody after the broadcast has any questions, they can certainly feel free to contact us, and we will reply with any questions. So without further ado, let's get into the webinar itself. So what is a containerized system? Any system can be built into a containerized modular system. Many people understand what a skid-mounted design is, where you have a series of processes put together onto a common, usually metal or thermoplastic or fiberglass support frame, and then is combined to form a system such as a chemical feed, pH neutralization, high purity water. When you're talking about a containerized system, you're taking that form of modularization a little bit further, and you're putting it into a fully designed system, which is itself enclosed, generally has environmental protection, lighting, utilities, and can basically almost be utilized as a standalone structure or building in addition to the system that it's actually housing. And the benefit of this is, or at least one of the benefits is, a containerized system can completely and by itself be a standalone process that can be added into any building structure and still without having a direct impact on the building or facility itself where it will be installed. So what are the key advantages of containerized systems? Minimum to no downtime of an existing process, which is really one of the big points of these systems. When you have an application, especially in a critical application, you cannot afford to have significant downtime. Taking a system offline, performing construction on site, tying in, this allows you to build a system in a module and then have it basically set in place, pre-tested and prefabricated ahead of time. Then all you're doing is making simple connections to your existing building or processes. So your downtime is reduced significantly. This also has no impact on the existing building structure. If you have a building or facility which is extremely busy or doesn't have direct access, this allows you to build a complete module that doesn't impact that space. It saves on the interior spacing. For example, if majority of your space is a clean room environment, this would allow you to build a module which can be located outside of that. It also allows for segregation if you have, for example, hazardous storage, and it can be implemented fairly quickly. There's no setting up construction sites, there's no demolition typically involved or large scale demolition. You can basically have an entire assembly built in a modular configuration, brought to the site, and then hooked up without basically done completely offline without any kind of operational impact, site planning, building permits, modifications, and really just a very simple way to basically expand your operations. So these come in a lot of different styles and shapes. And really the type of system, the type of containerized structure that you use or envision is kind of driven by a couple of different factors. One is really the size of the system you want to implement. We're going to talk about this a little later in the talk, looking at a few different case studies, and you're going to see that really different structures apply to different types of systems. Not universally true, but certainly an option. And also, obviously, space requirements, and also generally specifications or requirements of the site. But there are four primary types of containerized structures: a modified storage container, structural cabinets, modular buildings, and then portable clean rooms. Portable clean rooms is kind of an interesting one, which has really come to the forefront recently, particularly given the current medical climate, whereby you can basically fabricate a number of individual clean room modules that can then be reassembled into the field. These modules then allow you to essentially have different utilities, like almost on a super skid based structure, be loaded into them, and they can then be utilized as a means of, then they can basically be utilized as basically a mobile lab setup. The other ones are a little bit more fixed in place and obviously dependent upon size. But portable clean rooms is certainly becoming a growing industry, particularly in the pharmaceutical and the vaccination markets around the country and around the world. So what typically is involved? So as everybody knows, with a skid-based system, you have a series of processes, and you have a single point connection for power. Generally, you have a control panel. System is pre-plumbed and pre-wired. When you're moving into the world of containerized systems, the list of what's involved with your system grows quite a bit. Generally, you have full environmental controls. This is an important one because one of the primary driving forces for using containerized systems is the need to have a system located outside. And if you live in an area that could have more extreme weather or could have freezing temperatures, the cost and the impact of doing heat tracing in that type of a system, can certainly be, and is not always convenient or necessarily practical. A lot of the systems, for example, that we get involved in have special chemical handling. They can have large thermoplastic tanks. They're designed for acids and bases, and they're designed for corrosive chemistries. And that's not always practical to be able to insulate, heat trace, maintain different chemical tanks at different temperatures. Putting this in more of an environmental containerized system is beneficial. It also saves the time on site of having to build, say, an outside building, because you can basically have the entire system built and tested as one assembly, rather than having a skid built and then having a building built and then having to put them together. In addition to the environmental controls, chemical resistant lighting comes into play, leak and trench drains. Again, when dealing with chemicals or wastewater or even high purity water, that you definitely don't want to have any environmental impacts from having a containerized system outside of your building. Special ventilation requirements. This is both true for usage of the building, for some level of not really occupancy, but for operator use, but also if you're dealing with chemicals in the building, to have the ability to, have the special venting requirements. Utility outlets, again, for operator use, chemical spill protection. There's a lot of different door configurations for these systems, which we're going to look at here in a few minutes. And then also, there's a whole sort of range of sizes. These things can run from very small, something as big as a desk, essentially, scaling up to full containerized systems that could be up to 60 feet long. The primary limiting factor on a containerized system is you don't want to break it too much into more than maybe one or two modules, obviously, so shipping requirements. Really, as big as you can ship it is basically as big as you can make your container in a realistic fashion, which is why shipping containers are often utilized for this purpose. They kind of give you a set footprint or design that can be utilized when doing these types of applications. And, high tops are available, but you're generally, limited, by and large when doing big systems to the size of a container. And that becomes very relevant when you're dealing with some of the bigger systems that ultimately get containerized inside of these systems. So what kind of systems can be containerized? Really almost anything can. pH neutralization and wastewater treatment, filtration, lift stations, control or MCC enclosures, chemical feed systems is a big one. Waste storage is also very prevalent with these types of systems. So you definitely have a lot of different applications, and these different applications are obviously utilized in container systems in a lot of different ways. So what we're going to kind of do is now we've kind of talked a little bit about a lot of the different reasons why you would use containerized systems. What we're going to do now is we're going to look at a couple of case studies in some specific systems to see why they're done in a particular fashion and why these different types of containers were utilized and some of the different options that come into play with these types of systems. Before we move into that, though, we are going to just do our quick poll question here. Everyone wants to take a couple of minutes and just kind of fill that out, and then we will move on to the next section. All right, so our poll question was in regards to obviously what are the primary advantages of using a containerized system, and in reviewing, really the answer is obviously A, all of the above. Whether it's lack of impact on a building structure, saving space inside. Really, there's a number of different reasons why you'd want to move in that direction. And clearly, what we're going to highlight here in these case studies is a number of different reasons why this makes sense as an application to do. So first, we're going to talk a little bit about chem feed systems, and you can kind of see here in the imagery on the presentation, chemical feed systems are one of the most common systems which are placed outside. That's because a lot of times they're utilized in a very large variety of applications. We're pumping into a system we're pumping into is not always going to be practical as power plant or different application. Chem feed is one of the most commonly located systems which has to be placed in different areas around a facility. What is it? What is a typical chem feed setup? Just to clarify, a chem feed setup consists of a pumping system, where that's a metering style pump, peristaltic pump, air operated pump, which is designed for precision chemical injection. They often have accessories to the chemical they're utilizing, such as pulsation dampeners, back pressure valves, calibration columns, and controls. And they're configured in a number of different ways and different configurations, such as simplex, duplex, and triplex. And all of these different systems can be combined with a number of different chemicals and applications. Those include municipal water, disinfection systems, sodium hypochlorite, pH adjustment, wastewater for food and beverage, institutional clean water. Here's a couple more examples of a chemical feed system. But again, because you're dealing with the nature of a lot of these different chemicals, it does become very important to make sure that they are properly contained and that they are properly environmentally controlled, because obviously temperature can have a lot of impact on some of the sensitivity of the chemicals, the piping which is involved, whether that be PVDF, polypro, stainless steel, as well as freezing concerns. So there's a lot of different variables that come into chemical just based on the nature of what these systems are. And obviously a leak or some kind of environmental impact on these systems can be quite catastrophic for the site from an environmental standpoint, which is why these systems are one of the most common systems located in exterior environments and need to be containerized. They often have to be utilized to pump into specific points in the process, which isn't always practical when looking at it, as far as building a large outside building or structure. It's often beneficial to be built in more of a modular containerized design. So one of the simplest forms of a containerized design is like a chemical hotbox enclosure. And these are generally fiberglass, or they can be stainless steel in this case. And these are simply small boxes designed to keep a chemical feed system environmentally enclosed, protected from the elements, freeze protection. They can have leak protection in them as well. As well as and even some interior lighting. You typically have louvers and devices like that, which can also be utilized in these systems. So you can kind of see here, In the video, just kind of showing a few different examples here. This is really what a hot box, chemical system is designed for. And, this is really what they're utilized for. And in this particular example was actually for a fertilizer plant, which was located out in Oklahoma. Freeze and frost conditions were very relevant in these types, in this application. So it was very important to do this. But again, it wasn't considered a particularly hazardous chemical that was being utilized. So really, this was mostly for just environmental protection. But because these were located on different locations around the plants, they all had to be outside in that particular environment. When dealing with more hazardous chemicals, you can move into a more of a modular building design, which is what you can see here. This is obviously more of a modular building design as opposed to more of a hot box or just basic environmental enclosure. In these types of applications, you have segregation, for example. In this case, you have two different chemicals that, if they do combine, can be reactive. So they're 100% segregated between the two of them. Chemical safety showers can be built in. And that is true quite a bit with containerized systems. Very often they will have auxiliary equipment such as fire suppression or chemical safety showers, or maybe some specialized venting, depending upon what their actual application is. This one here also has a bottom drainage area in case there's any spills, so that you actually have some level of leak protection in your system. Environmental lighting is included. Then you can see on the exterior here, you have some warning lights as well as the actual HVAC system, which is really designed more for the chemicals themselves as well as for the operators for ease of convenience when utilizing these systems. Kind of a different take on the chemical system. This is actually somewhat common as well, is a mobile chemical injection system. So these come in a couple of different varieties where you have either more of a trailer-based design, or either that be a smaller unit or something like you see here, which is actually utilize a drive or basically mechanized move a chemical injection system around the site. And there are some differences with these. Obviously, these are built onto a unit which can actually be moved, by a vehicle. They often, all the tanks in them have to be DOT rated, and you do have to have obviously non-hardwire power supply to these, whether that be a generator-based system, if it's a more remote site, or you have more of just a plug-in system, specialty for 460 volt or 120 volt, whatever the actual power requirements are for these systems. In this particular example was a hydrofracking disinfection system, which was driven around different gas sites to allow for purification of the water, which was being utilized in a fracking application. This is just one example. They also use these on things like power plants, for example. Well, they use mobile units to actually clean turbines on the site. So this is just kind of a little bit of a different take, but very similar concept. You basically have a fully containerized unit. It's mobile in this case. It has HVAC involved, but it does have to just meet certain DOT requirements so that it can be mechanized then and moved around a particular site. In addition to chemical feed-based systems, you also have chemical storage, or even in this case, hazardous-based storage systems, which we're going to talk about here in a second. And these differ a little bit, obviously, because in these types of environments, you're building a system which is designed to hold some kind of a hazardous chemical. And it's often beneficial to locate these systems outside, because very often these types of chemicals need to be hauled off site for treatment. So storing them inside of the building then has to require you to have somebody come in, haul them out. This allows you to transfer them into more of an environmental safety enclosure, which can then be accessed from the outside to be removed for chemical safety, or pumped out for chemical safety. Now, what is a hazard? I mean, hazardous chemicals range across almost any industry. And it really depends on what the chemical composition is. This can be something from a solvent, which typically hauled off site and burned, heavy metals and mercury, which is utilized in different application, emulsion-based solutions, or things like chromographic solutions, biologics, and even very highly corrosive acids and bases, all need to have special handling requirements. And often beneficial, especially if you're dealing with these in low volumes, to have them brought to a containerized base system off site. These typical systems, the main driving force, these are not totally accessible systems necessarily, although they currently can be built that big. They're generally built to house, several drums, for example, or several tote-based systems, as we saw in the previous slide, or a single large tank, which can then have the actual reagent, the actual waste taken off and removed. These do have environmental controls, obviously, because they generally are located outside. They also have special venting requirements, particularly if you're dealing with a class one, if you're dealing with a hazardous chemical, which could be class 1, div 1, or class 1, div 2, as well as some of them also having fire protection based systems as well. These systems are generally relatively small. Again, if you're dealing with large volumes of these chemicals, you generally go to more of an outside, large scale storage tank, for example. But certainly for very small scale systems, this is a very practical idea. And these can be found in really any number of different industries, from just general industry to pharmaceutical, food processing, paint, research, semiconductor, really any kind of waste stream that can't go down the drain, but it's generally generated in fairly small volumes. Is certainly a candidate for a type of system like this. As you can see here, just a couple of examples of these types of systems. Air valves that could have nitrogen pressurization as well. But they're just, again, more of a cabinet base as opposed to more of the true kind of bigger kind of chem feed or mobile systems. It's really what the kind of driving point of this is that depending upon what your application is, how a containerized system is selected and built is really kind of a big driving point. Which we're going to talk about even more when we talk about some of the larger systems. Most of the ones we've looked at so far have been relatively small, smaller containers like this, which might occupy an area of, say, 4 by 6 by 8, some very small dimensions. Even the chem feed systems can even be in smaller base designed. Some of the larger systems obviously get to be 50, 60 feet long, just based on what you're actually putting into these systems from an equipment standpoint. One of the most common systems which is utilized in a containerized based system is a pH neutralization system. And if you think about it, that makes a lot of sense, particularly if it's a system that's just being added to a particular process or something which is being added as a retrofit application, because almost all drain lines run outside of the building underground. And if it's not practical to treat the waste inside of the building, or for new processes added in, it can't be tied into an existing drainage line or pH system. It's often practical to then intercept that and then treat it in its own modular building outside. But first, what is a pH neutralization system? A pH neutralization system is one of the most important elements of any building. Any substance that can be dissolved in water can have an impact on the pH. So whether you're dealing with things like, higher education, public health labs, industry, general industry, pharmaceuticals, they're all going to generate waste streams which have an impact on the pH that needs to be treated prior to discharge into the sanitary sewer environment. So pH systems can really be found in a multitude of different industries. And because of the chemicals involved and the corrosive nature of these, they can be kind of hard to just put outside. You put them outside, you obviously need to heat trace them if you're in a cold environment. If you're using things like caustic soda in them, it's not very practical since you have to maintain a fairly high temperature for its use. So it makes a really good candidate for a pH treatment system. But as a result, there's a lot that goes into these systems, at least from a size perspective. You have treatment tanks, you have agitation, chemical injection, controls, and the standard residency time for a pH neutralization system is 20 to 30 minutes. As a result, if you have a 100 GPM system, you could be looking at something you could be looking at a containerized system that has to hold a 2,000 or 3,000 gallon tank, have proper access to it, have the reagent chemicals, have the control panels, and then have to be able to meet all the different requirements, whether it be NFPA 79 or clearance for lockout, tagout, or chemical changeout. And this is really what drives these systems to be built, obviously, in much bigger applications. Very often, even modular buildings, as we're going to see, or into more of the modified, modified shipping containers, when compared to some of the other systems we just examined from the chemical feed and in the waste storage perspective. One of the most common systems which is utilized in these types of systems is an ACS style system from process equipment, and these range in size up to about 300 gallons per minute. Again, they have large agitators that stick out the top. Another thing to consider when building a containerized system is access to the top of the tank and access to be able to remove things like agitators from the tank. Um, Having the ability to access pH probes or other instrumentation that goes into the large treatment tank. This all plays into why the ACS design, with more of its ergonomics for circulation and having that kind of lower level access that you can see here in the image on the right, becomes very critical for these types of systems. And that's one of the main driving points that people want to look at, which is why it's often utilized with these types when utilized in containerized systems. But they're very big. They come in single and dual stage configurations. They can have lift stations. They can have equalization tanks, large PLC controls, and some of the bigger ones. That tank can range to be 13 to 15 feet long, which doesn't sound, that big when you're thinking about a shipping container. But putting the tank in, the reagents, the control panels we're going to see, everything needs to be kind of laid out in a way that also makes it ergonomical and practical. And also requires the ability to put in other ancillary equipment, which may be required for the system. These things can't, that really laying these out does become a little bit of a kind of an art and sort of engineering task, to allow them to function both, properly, and allow them to be utilized, allow them to actually really serve their purpose as a pH neutralization system. One system that was completed very recently by Bird Process Equipment, this actually went back into the springtime, was for the Department of State and Health Public Service Laboratory for Austin, Texas. And this is actually one of the largest state laboratories in the country. And obviously that became very critical, this past year, during the pandemic. And they needed a way to basically build in a pH neutralization system without having really any primary interference into their operation or really even that much in the way of access into their facility, but still obviously accomplish their goal. And that's really where containerized systems do begin to shine. You're going to have is when you have an application and you want to implement something quickly, and you don't necessarily want to have direct impact into your facility. And that's really what these units were designed for. In this case, they did go with a level of redundancy in these types of systems, basically having a setup, by the reviewing with process engineers as well as the state. Um, two different basically flow through almost ACS style batch systems, which can be fed from their existing outside equalization tanks. And you can really see here, kind of looking at the image, looking at some of the photos of the system as it was being built. That's what these tanks begin to look like when put into a modular building design. In this case, it was a modular building design as opposed to a modified container-based system. That was really a requirement of the site. There are different specs that can be utilized for modular buildings and containers, and these can certainly be followed if required. And some states do require almost like a building permit for these, because oftentimes these systems are kind of looked at not as a building, but as actually like a modular system. So even when though they have access and they have roofs and they have environmental, they aren't considered quote unquote buildings. That's one of the benefits of them, is you can kind of move away from actually having to implement, a full building code and plumbing and all of that. And really what you have here is just a system basically in a box. So you can kind of get away from some of that. But sometimes people do require just different states. And obviously, this being a government lab, there was some different requirements in this case, such as things like fire suppression systems and things like that. And some level of building permits that still had to be pulled for this application. But that's how much bigger these systems get when you're talking about more of a pH-based system. You can see kind of the outside of one of the containers here. In this case, due to room allotment, they ended up with 2 containers as opposed to one large one that could be then be installed on site. The 2 containers themselves, you can see there's a lot of different options that can go into these types of larger systems, just like you had in some of the smaller ones. And you have outside warning lights, as you can see here. You have double swing doors. You can have roll-up base doors. You can have leak drainage in these things. They have different coatings that can go in the inside of the tank, inside of the system. Again, very relevant from a safety standpoint. If you have any kind of a leak, or somebody's moving drums of chemistry in and out of these types of systems. You can see in the upper corner here different roof axes to access the top of the tank or to allow for the removal of things like agitators in the system. So again, there's a lot going on in these systems. They also have to include things like lighting and utility and other things that allow them to actually be serviced properly within the actual system. Some people even affix outside lighting to these systems as well as a means to actually illuminate the area around the actual system. Looking at the system in particular, as I mentioned before, this was brought into a public health lab environment where they basically had some existing equipment. You can see here on the right, they had a lift station that was feeding into an equalization tank and then the actual transfer pump systems, which fed into basically 2 different redundant pH neutralization tanks here with a common reagent injection, and then a secondary treatment tank here as well. And looking at the inside of the containers here, you can see the tanks obviously occupy basically about half of these units. You have top access here located right here above the agitation. Back swing doors so the tank itself can be removed if it ever has to be for maintenance. And really the front section of these then becomes the primary work and operational area. All your instrumentation is located on this side of the tank for access. Your common effluent drain system is also located here. Here you have your fire suppression system, control panels with proper access for lockout, tagout, junction boxes as well. Very often with these types of systems, you will have you will have a segregated environmental control, and that can vary considerably based on the location of where you are and the requirements, exactly what you need. But generally, some kind of an air conditioning and heating based system. Obviously, in warmer climates, air conditioning is certainly more important. Putting a metallic box outside with the system, with the sun beating on it all day, can make that obviously make that environment very warm for operator. But at the same time, if you're where I live up here in the northeastern part of the U.S., we have a lot of concerns about freeze protection, snow loading on the systems. That kind of all comes into play here as well. But very often these systems will have a common power supply to a main control system, which will control the actual system involved in the system, as well as power like a 120-volt box, which will then be utilized also for the utility and the lights in the actual system. And then very often you'll have a separate power feed for the environmental controls. One of the reasons to really do that is so that if you have any kind of an issue within the system and you hit the e-stop button or shut the system down, you don't actually shut down the environmental conditions inside of the building. In that case, you're only shutting down the actual processes inside of the building as well. And it's also another reason why sometimes people actually put a separate power feed also just for the utility. So you can kill the system, but leave the lights on, leave the HVAC system going, and then allow you to service the system properly or perform any maintenance or shutdown on the system while doing that. So here you can just kind of see here kind of a brief video that sort of highlights This is the actual building location. Obviously, this is, public health labs have come to the forefront recently. Um, but again, like all major, health labs, pharmaceuticals, they all have been generating obviously a lot of waste. And there's still obviously environmental concerns that need to be taken into account with these types of systems. This really makes it kind of a perfect situation where you would utilize, where you utilize a containerized base or modular system. It can be pre-designed, it can be pre-tested, brought to the site, and then all you basically need to do is tie it in, which in this case they were able to do over the course of like a weekend, actually, in this case. And here you can see how these systems really go together. Containers themselves are built, but the system is actually designed all as one piece so that there's no issues with things fitting into them. Wiring and lighting, everything's really largely mapped out ahead of time. So when the finished product is done, you end up with really one fully complete system, which can then be utilized. There you see some of the louvers for some of the HVAC equipment, some of the shielding for the chemical injection pumps as well. So really overall, it basically comes out just like you do the skid, but in this case, now the entire system is integrated into, a full module that can just be dropped in place. There's no pouring pads or any of that kind of stuff for a skid. Dropped in place, anchored. Seismic can sometimes come into play with these systems and then get really like ready to go in that case. So just one last example here, showing a little bit of a different design. Again, it's a pH neutralization system. This is for a pharmaceutical client. This is a little bit bigger system than that one. This is designed for about 150 GPM, high voltage, low voltage panels, full effluent, environmental controls, drainage trenches for environmental protection. Here you can kind of see how systems are built, the back of the tank being loaded into the container in this case. And this is how the container lays out. This was one large container. This was almost about a 50-foot container in this case. They had some different ancillary equipment that they were looking to implement into the system. And as a result of that, they have a lot of front storage space here. You can see this is, again, your treatment tank. You have your top accesses over this particular area, roll down doors, common effluent. You have your reagents, but then they also wanted some additional storage here. You have your 120-volt load center here. This is what I was referring to for all the utility applications and transformers. And then you have your basic control systems for the actual system. Here you can see these are the type of hatches that I was referring to for the system. One directly over the agitator for removal. And then really one here as well, just for access purposes. And very often these will also have a door here as well to basically push open. Again, the treatment tank is almost always located on one side of the system to allow it to be more easily removed for maintenance purposes as well. This is kind of show a little bit of what goes on in these systems here. This is the lighting layout and the duct design. You have emergency exit sign lights. This is your lighting path. You have, basically have LED lighting here, which is acid resistant going down the whole system. You have your overhead AC ducts in the system. Your 120 volt. You have your different 115 outlets, outside stack lights. Generally, you can see what's actually going on, or at least visually see what's going on inside a container when looking at the system from the outside. So there's a lot of this is kind of things that really go into these containers that allow for a bit more of a complete system in that case. But this is kind of some of the sort of periphery outside of looking at just what the base process is. But you can really see as you move into some of the bigger systems, like the pH systems, these things get a lot more involved than they do with just say comparing to a lot of the more basic chemical feed systems, which you would typically see in typical chemical feed systems, which are obviously considerably smaller in these cases. Some of the support equipment that oftentimes goes along with these types of systems is something more like this, where you have kind of just an outside enclosure here for maybe a pump support to more of a containerized base system. And then this is what the system actually looks like. You can see here different painting options are available. This is the overhead door. This is a roll-up door, I'm sorry. On this side, you have some HVAC or indoor window connections. This is more of a modified shipping container design, so it's a little bit different, but serves a very similar purpose. Again, highs are fabricated, the tank's getting loaded inside of the system. And looking in the inside, you can see here, these are the upper access hatches I was referring to, the LED lighting. You have this kind of a little protection pan here, and then some of the other protection here for the chemical feed piping, spill containment for reagent tanks. Different flooring options are available on this side here. You can see this is all chemically resistant polypropylene. This is all diamond deck for non-slip resistance. So it really depends again on kind of what type of system you want to put into here. The chemicals or different devices which we utilize to help determine what the best options are. So that is the end of our seminar, is the end of our Fluid Series webinar. Again, to really kind of sum this up, containerization is an option that can basically be tied into almost any system. And there's a number of factors that determine either A, the practicality of doing it or whether or not it makes sense. What type of container depends largely on the type of system, the size, what's going into it, and then also really the operation of it. Is it going to be more of a clean room environment? Is it a waste treatment system, chemical storage? So, containerization is a broad topic. And today we've kind of highlighted a number of the different case studies, a lot of different reasons why you do it, but it is application specific. And it is also very important to kind of look at it from a couple different perspectives and work with and obviously talk to an engineer, people involved. They really determine what's the most practical solution for different case. For the example that you're looking at. Please stay tuned for 2021. We will be posting that soon for our next webinar series. And we do have a few questions here that I'm going to go through, but if I don't get, but any questions that you think about afterwards, please feel free to send those over, and we'll certainly get back to those as well. So getting into the few questions here, do you use ISO? ISO is often utilized. ISO is often utilized for the actual building containers themselves in some cases, but it is not utilized for the actual equipment that goes into them because there's so much customization that goes on with those. So it's not actually practical to do that. But if you are looking at particular modular designs for the buildings that these can actually be built into, then that is an option that can be utilized, but not always. Sometimes they themselves are also customized to the fact that ISO is not going to be practical in those cases. Next question, can the containers be built to particular specs? Yes, they can. There is really every one of the applications that these are utilized in. Typically the container is either an option or something that can be specified as part of the system as well. And we've kind of done it both ways. We can certainly make recommendations as to what has been practical or has been done in the past for the type of system. But a lot of times there are very specific specs, either from the end user or the engineer or the architect that's involved in the project. And these systems can be built to, again, a variety of specs where they go from very small systems up to, again, like the one I showed you guys for the Texas State Lab, that had a very particular specs, paint coating, corrugation pattern, seismic and lagging constraints, etc., that had to be built to. So there definitely is a lot of options when it comes to that. Do we do the interiors and environmental controls? Yes, we do. So very often the environmental controls are based on what goes into the system, as far as what the actual treatment process here, the chemical, if there is a particular temperature requirement. If not, they'll generally be built to more of an operating conditional level based on where they're going. So the environmental design does vary from application to application. So, for example, if you're building a system here in Connecticut,
which is where I'm based out of, or if you're building a system in, say, Southern California, you're going to have some different environmental requirements that go into these systems. So that typically is done based on location, the size of the unit, as well as what's going on. If you, for example, some people only want to maintain at a certain temperature. If you have a particular process that requires an elevated temperature, such as like a large degree of caustic storage in the system, then you need to account for that. Typically, one of the bigger things isn't so much heating, it's actually cooling it. If you do put a modified storage container with a system outside, and for example, the southeastern U.S. with the sun baking on it all day, it's really more of a concern of air conditioning and ventilating the system, which comes up more and more often. The other thing that comes up occasionally is venting. And that's a big one with a lot of the hazardous storage, where they actually need a separate vent-based system, in addition to just the environmental controls based on potential off-gassing out of your system. As far as the interiors go, again, there is some differences to that as well. Some people will just use more of an insulation-based. If aesthetics is important, sometimes they'll actually put in a bit of an acid-resistant fiberboard, thermoplastic walls, or even something as simple as sheetrock. I've seen for these types of systems as well. It does ultimately depend on what's actually going to go into the systems very often for that. As far as the question here, what is the allowable inside height and width for these types of units? If you're working with a modified storage container, typically they're 8 feet wide, and you basically use a high top, so you can go up to about 12 feet in those cases. But if you're going into the more custom realm, that there is some variation allowed in that, but again, typically since these are shipped over the road, you do have to basically keep them within the requirements for shipping, which basically keeps it to, with the outside wall thickness, less than 9 feet and basically no higher than 12 feet. If it's more of a cabinet-based system, they do tend to vary a little bit more because they're a little smaller and more configurable for shipment. So they can be designed to kind of a number of different dimensions as well. Last question here. What about different safety features? You mentioned fire suppression systems. Is that required? That's really an insurance and sometimes it might actually be a state or local requirement if you do require safety systems in these systems. Again, most of them don't fall as building codes, so they don't have the same requirements as a building code would be, because really they're really looked at kind of one of two ways. The most common one is that they are a system that just happens to be enclosed. The other one is you're looking at a building that contains a system. The former is generally what most people look at these systems as. And so it's basically taking the place of either heat tracing the system, or putting it inside the building. It's basically a system which is just integrated into more of an environmental-based enclosure, and thus is not subject to building requirements for things like fire suppression systems and things like that. I'm not saying it's not a good idea to put it into it, but it does change the fact that the permitting for them doesn't necessarily require them to be permitted as an actual outside structure. In most cases. So that's kind of the big one there that oftentimes comes up. Well, that's all the questions so far. Again, if anybody has any more questions, we'll stay on here for another minute or two. And if not, if you think of anything afterwards, please feel free to email us. And I wish everybody a good end of the year. Thank you very much.